Good afternoon, everyone. So today I'll be talking about surface layer temperature inversions, which are found in the Bay of Bengal, and their main characteristics and their mechanisms. So first of all, what is a surface layer temperature inversion? It's nothing but a subsurface warm layer, which is kind of sandwiched between a top mixed layer and a deeper isothermal layer or deeper cold water. And to draw the profile, if this is the ocean surface, and this will be the temperature stratification, and this will be the salinity stratification. So you see this is the inversion rate. So we have here inverse thermal stratification, and it occurs in conjunction with barrier layers. These layers are usually found in the Bay of Bengal during winter time, and they have a warming effect on the surface when the wintertime cooling is happening, which means that the heat flux is negative and the Bay of Bengal is undergoing surface heat loss. And what are the formation mechanisms? Well, people have argued that formation mechanisms include the role of surface freshening, which is the strong salinity stratification in the Bay of Bengal because of the fresh water due to rivers and precipitation. Then there is subsurface warming by penetrative solar radiation, which penetrates the surface and warms the subsurface here. And there is surface cooling as well. So what are the prominent formation mechanisms? So I'll be talking about that as well.
It's not moving. The slide is not moving.
Ma'am, is it moving now?
It moved. Now it has come to the second one.
Okay, fine. All right. So this is the profiles followed by, these are the profiles obtained from following a single Argo float. And this is the temperature inversion. These are the temperature and salinity profiles at this particular location, 91.27 east and 16.48 north. And this is during January, 22nd January 2017. So you can clearly see here, there is a subsurface warm layer beneath a mixed layer. And you also have a stable salinity stratification throughout. This is very characteristic of the Bay of Bengal, and especially as you go more towards the northern Bay of Bengal, you will find sharper salinity stratification. And this is a profile during one time, and here is the same Argo float, but it has been tracked over 3 years. So you can clearly see 3 depths are being plotted. One is the mixed layer depth in red. Another one is the isothermal layer depth, which is nothing but the depth at which the surface temperature equals the temperature at, let's say, some particular depth here, which includes this thermal inversion as well. And the mixed layer depth will be only till where both temperature and salinity are almost homogeneous. So during winter time, which is around December, January, February, again December, January, February, you will see that the isothermal layer depth and the depth of 23-degree isotherm is deeper than the mixed layer depth. So this indicates the presence of an inversion layer, and the inversions are marked by these color contours here. And these are the magnitudes of the inversion. So you can see more stronger inversions up to 2 degrees Celsius occurring during peak winter time. And similarly, we have the barrier layer thickness and the salinity contour from the same Argo float. So you can clearly see that during winter time, we have again very sharp salinity stratification here, which helps in maintaining this this structure. I'll give one more plot for clarity. So this plot is again by following a different Argo float, and this Argo float has been the track of the Argo float is plotted there. You can clearly see the Argo float from January, February, and March, and these are the temperature and salinity contours. And these are the profiles at again one particular time in January at 19-degree north at this particular location, 89 east, 19 north. You can clearly see the temperature inversion present here beneath a mixed layer. So this is the inversion layer. And this whole layer is called the isothermal layer. And isothermal layer subtracted isothermal layer minus the mixed layer depth gives you this inversion layer. Oh yes, that will be better. Sorry. Right. So the isothermal layer, which extends up till what 110 meters, 110 meters, this subtracted this minus the mixed layer depth, which is around 20-25 meters, will give us the inversion layer. So we can clearly see this inversion layer extends up till around 70 to 80 meters, especially at 19° north, which is quite north in the Bay of Bengal, very close, not very close, but like closer to the river mouth. And these are the contours of temperature and salinity. So we can clearly see that the inversion layer is strongest during winter time, which is January and February. And as the heat flux begins to increase as the springtime warming starts, this inversion layer also gets weakened. The temperature stratification or the temperature inversion is not very strong in March. And so is the salinity stratification. The salinity stratification is stronger in January and February, but it is not as strong in March, which also gives us a hint as to why this inversion layer is stable in the first place, because it is being supported. One of the reasons is it is being supported by this very strong salinity stratification. So now here this paper Tharatil et al. 2016, they have taken 4 Rama buoys at 4° north, 8° north, 12 and 15 degrees north, and they have tracked the inversion layer for each of these locations to provide a spatiotemporal analysis of how the inversion layer of when and how much strong is the inversion there. So as we slowly go towards the north, these dashed lines indicate mixed layer depth, and these solid lines indicate isothermal layer depth. We can clearly see as we go more and more towards the north, the gap between these isothermal layer depth and the mixed layer depth increases. In the south, the mixed layer depth and the isothermal layer depth are not as much different as compared to the north, and the dots here indicate the magnitude of the temperature inversions. So it's not clear in the slide here, but blue dot, and as you go, as the color of the dots change, you can clearly see the magnitudes of the inversions, magnitudes of the temperature inversions, and the temperature inversion is maximum around February in the northern Bay of Bengal. And these dots are present at the center of the inversion layer. And at the center of the inversion layer, by the center I mean where the center of this particular inversion layer. So you can clearly see that as you go more towards the north, the inversion layer also becomes deep, and the magnitude of the inversion also becomes stronger and stronger. One more thing is clearly visible in the salinity stratification here. As you go slowly and slowly towards the north, the salinity stratification also increases, which brings me back to the point that strong salinity stratification favors stronger inversion layer and deeper and stronger and deeper inversions. Right. So these are the seasonal variation of the magnitude of the inversion, which is delta T, the inversion layer thickness, which is LT, and these are the percent occurrences, which is nothing but the seasonal variation, and for different latitudes from different Rama buoys, plotted from October to March. And one can clearly see here that in the northernmost Bay of Bengal, which is at 15° north, you have more percent of occurrence of these inversion layers, as well as the magnitude of these inversions plotted in blue is quite large. It goes up to 0.8 degrees Celsius, around 1 degree Celsius, even if you go even further north. And the thickness of these inversion layers, which is plotted in red, is approximately 60 meters, 62 meters, and so on and so forth. And the peak occurs in January. You don't find any inversion after March, April, and May. You don't find much inversions because the surface layer also tends to warm and the inversion layer is not exactly sandwiched. The heat is increasing. Heat content is increasing. However, as you go slowly and slowly towards the south, the percent occurrence of this inversion layer also decreases, as well as the thickness and the magnitude of the inversion also decreases. And the maximum inversion occurs during winter time, which is one of the most prominent features of the northern Bay of Bengal. And to illustrate to illustrate further mechanisms, I'll be just taking this particular Rama buoy and doing analysis from there. Now we come to the causes of what causes this inversion in the first place. So here we have plotted the normalized or the distribution of SSS, which is sea surface salinity, with the percentage of occurrence of the inversions. And the red color here indicate the profiles with inversion, and the blue color indicate the profiles without inversion. So you can clearly see wherever there is strong salinity stratification, and by strong I mean less than 31 PSU, less than 31 PSU of the surface salinity. Whenever there is strong salinity stratification, it is usually accompanied by inversions. When there is moderate to weak salinity stratification, moderate to strong salinity stratification, which is around 31 till 32.5, you can see that there are some inversions not as prominent as the ones where it was strong. And after 33, you have less inversions and more non-inversions.
The percentage, then the two should add 100. Why it doesn't have? There's something else which is third category, obviously. Right?
Yes.
So what would that be? This is major inversion, non-normative.
So I think all the red ones add to 100, all the blue ones add to.
And around the, okay, expect to add up all the numbers. Okay.
All right. Yes. So that's correct. Actually, yes. The inversions, I mean, we have taken the whole period for inversions and then taken the percentage for each of the particular.
Okay.
Yes. And profiles with delta T greater than 0.18 degrees Celsius, this is just a criteria taken, are only as treated as temperature inversion. So this gives again a hint as to the inversion might be strongly related to surface freshening. And to quantify the other terms which might be important in causing this inversion, a mixed layer heat budget analysis has been done, where the mixed layer heat or the mixed layer temperature or the SST tendency, the mixed layer temperature is taken to be SST itself, is plotted along with the horizontal advection term, the atmospheric forcing term, and the remainder term. The remainder term includes the contribution from all the processes. And it has been plotted for 3 different years, which is 2008 to 9, then 9 to 10, and then 12 to 13 for the Rama buoy at 15 north, which was the northernmost Rama buoy. And here, the thick portions of the lines indicate the presence of inversion. And especially during December, Jan, February, especially during January, you see that the SST tendency is negative, which is plotted in this black line. It's a little negative, and the remainder terms are positive. They are positive. And why is that? And what does that really mean? So if the profiles are like that of temperature, if you have surface cooling going on, which means that the ocean is losing heat, the profiles will become somewhat like this. So which means that the surface is cooling. However, in an already cooling surface, the temperature inversion also acts to supply heat upwards, thus dampening the effect of cooling. So the remainder term here, positive, indicates that the surface layer temperature inversion has a tendency to warm the mixed layer because the heat is being supplied from the subsurface to the surface. While the atmospheric forcing, if you clearly see the atmospheric forcing, which is in the red, it's negative, which means that overall the ocean is losing heat. The atmosphere is trying to take the heat from the ocean is losing heat, but the cooling tendency is being dampened by this positive upward heat flux due to the inversion layer. So this is also one of the mechanisms, vertical process mechanism in which the inversion layer actually tends to dampen the effect of the cooling. Right, and this is a scatter plot of the remainder term, which denotes the vertical processes with the magnitude of the inversion. So it's the correlation is quite good. It's around 0.48. And hello. All right. So here we can clearly see in the non-inversion case, which is plotted here in blue, the remainder term is negative. And what does negative mean? That it is trying to cool the SST. If we don't have any inversion, the vertical processes will try to cool the SST. In case we have inversion, the vertical processes will try to warm the SST. This is, and the stronger the inversion is, which means the stronger this negative gradient of temperature is, the more it will try to warm the SST. And the more it is being correlated with the remainder term, which is delta, which is degrees Celsius per day, which is the tendency. Right. So this plot again shows the same fact, but along with different kind of statistics showing that the surface layer temperature inversion tends to warm the SST. Right. So these are some of the basic mechanisms till now related, but one of the questions that I have been investigating is, and I've still not gotten to the depth of it, is how much contribution of the formation of this inversion layer is due to surface cooling, which is, let's say, Q cool, versus the subsurface penetration. The relative contribution of cooling heat flux versus the penetrative heat flux in causing this inversion layer, because it is the gameplay between these two which can create either stronger inversions or create weaker inversions. Because saline stratification helps to maintain the inversion that is accepted and that is given because we have strong salinity stratification. But what is the relative magnitude of these both processes? That I am still investigating. Right now, I'm focusing on that. So that's fine.
Any question?
That is inversion, non-inversion. Yeah. So what do you mean by non-inversion?
Non-inversion is where you don't have this negative temperature stratification. You just have normal.
Regular profile.
The regular profile, mixed layer and then yes, thermocline.
Yeah, I'm curious about all the complications going on, Bay of Bengal. What impact it has on the next summer of the SST? Ultimately, Bay of Bengal communicates with the atmosphere through SST.
Yes, yes.
So all this is very interesting as a problem in geophysical dynamics, but ultimately it must have some impact on the spatial pattern of temperature the next summer.
Yes.
Has anybody looked at how they evolve and what happened next summer?
Next summer, sir, I don't think people have looked at because
It must have an impact, right? Where
Yes.
more inversion.
it will have a data. Exactly.
It will
Because
be cooler next summer.
yes,
So what's looking at the issue is that what role Bay of Bengal is playing in monsoon is still not fully understood.
correct.
In Arabian, you know clearly. Arabian is SST correlate Indian monsoon very high. Bay of Bengal, no. So the question is, what the SST pattern and what impact it has on disturbances being formed there and how they evolve, all that is.
One thing which can come to top of my mind is in the South Bay of Bengal, where the inversions are not as much present, given the same springtime heating, it will respond less quickly as compared to the Northern Bay of Bengal. Why? Because in the Northern Bay of Bengal, you will still have transfer of heat from the stronger temperature inversion. In the Southern Bay of Bengal, the temperature inversion is not very strong.
Yeah, I understand that. Now, this inversion also related to what was the Indian monsoon.
Yes.
Right?
Yes.
So that probably will Indian monsoon affects this inversion, and the inversion next year what it does to SST. I
Yes.
think it's very important.
That. Yes.
Yeah.
But I don't think I have seen any study regarding that.
But tell me, how many coupled models are able to reproduce? Are they enough resolution to look at that layer?
Inversion layer, not really, sir, because this occurs in what, let's say 50 meters. And the inversions are of, let's say 1.5 degrees Celsius to 2 degrees Celsius.
No, but the model, the resolution to resolve it. Coupled. These days, we are not in touch with how good the
Not
results
sure,
are.
sir. I'm using large eddy simulations.
Oh,
So my resolution is 4
yeah,
centimeters.
yeah, I'm talking about GCMs.
GCMs, I think there are about 32 levels. Parag might know. 32 how many?
Yeah, but how many levels you have the top? That's important.
Yeah, that's. I don't have much idea about that. Many people who are running ROMs, they might tell
Down
something.
to 1%.
Really?
Near the top, you have.
Top 100. Afterwards, it's.
But this is sufficient to resolve that inversion. That's what I'm saying. Oh, no.
Did you see it in ROMs?
Yeah. Okay, very good.
Yeah, I'll
Thank you.
show you. Thank you, sir.